Hi there, and welcome to the first part of the Zero to ASIC course. Thanks very much everybody for signing on and getting involved. The way this is going to work is each part of the course is going to have a short introductory video, and so this is the short introductory video for part one, which is about MOSFETs, how MOSFETs are made, how they work, a bit about the Skywater process design kit, and looking at some standard cells. So let's get started with why we're interested in doing this. So I think for me one of the big parts is when you put technology in more people's hands, you get exciting, unpredictable innovations happening. And I think we've seen this with GCC and Linux and Arduino, and it's going to be happening with RISC-V, and the next step is open source silicon. So I'm very happy that you're along for the ride, and as well as learning how to make your own ASICs, I really hope that you're part of the vanguard of people experimenting with things that people have not experimented with. One of the really exciting things for me, or the interesting things maybe is a better way of putting it, about ASIC design and chip design is the huge broad range of numbers. So we've got very tiny numbers like the sizes of things. So if you're not familiar with nanometers, which is the scale that we're often working with, we've got meters, and then 1,000 times smaller is millimeters, 1,000 times smaller again is micrometers, and 1,000 times smaller than that is nanometers. And the nanometers is the scale that we're working at. We've got huge numbers. We've got $100,000 for the setup costs for actually building a chip, and that's one of the barriers that have been swept away by the Google Skywater eFabless initiative, giving us this free shuttle to experiment with. The market for ICs is huge, 500 billion in 2018 according to PricewaterhouseCoopers, and apparently MOSFETs are the most manufactured device ever in the history of humankind, 1.3 times 10 to the 22 according to Wikipedia. One of the things that was emphasized in this old school book, which I did find an interesting read if a bit dated, is that even back then people were thinking that it was a great idea to get involved, get experimenting, get hands-on, and that's a really good reason for doing this course and getting your hands-on and learning how this stuff works for real. There's lots of digital designers and even ASIC designers that I've spoken to that are only involved in one small part of the process and don't have an overview of the whole thing, and that's one of the great things about this course, is that we're going to cover everything from zero to ASIC, at a very shallow level, but at least you can see how all these things fit together. So digital computers need digital switches, and the first switches were mechanical, and then we moved on to electromechanical with relays, and then we managed to make them faster with valves and then smaller with transistors. And in 1954, we've had our first transistor, and by 58 we were putting multiple transistors into integrated circuits. We can see through the process of time how the number of transistors has exponentially increased, although we are getting to the end of that growth now, it seems. And the complexity of the designs has gone up. Let's take a look at a quick video. So here we've got an optical microscope zoom in of a chip, and part of the chip has been etched away, so we can see that there's actually a huge amount of plastic, and then to make the chip easy to handle by hands or machines. And then the bit that actually makes it work is this tiny little chip in the middle, and that's the actual bit that we're learning to make here. These gold wires are the bond wires that connect the lead frame, that's where the legs are, that we solder down onto the circuit board, to the actual pads, the in and output pads on the silicon chip. And now we switch to the scanning electron microscope view. We've got these big power buses here and stretching out across the chip. And as we zoom in, you see another set of parallel lines. So these are the standard cells now, the repeated small building blocks like AND gates and OR gates that are joined together. On the top you can see how they're all interconnected with these metal wires. And then underneath that we actually see the standard cells, with the top and the bottom being power and ground, and then the transistors, the MOSFETs that make all this work underneath that. And this is this tiny scale that we're working at here. So this, the length of the gate is one of the critical dimensions. And in this process that this chip has been working on is 1000 nanometers. And the Skywater process is 150 nanometers. So what is a MOSFET? It stands for metal oxide silicon field effect transistor, which is a bit of a mouthful, but it's a type of transistor attributed to two people in '59. These are the circuit symbols. If you're a maker or an electronic engineer, you'll definitely recognize these. This is an example of a MOSFET in a really big package designed for easy handling or dissipating a lot of heat for power electronics. And you often use them for switching on and off motors. And actually we've seen a huge amount of them used in brushless DC motors, like for drones, because you need to very quickly control the phase and the direction of the electricity through the windings. This is a cross-section taken through a MOSFET. So let's take a closer look here. We can see how the circuit diagram picture here kind of matches what the actual physical structure is. So we have the source and the drain connection, so that allows the current to flow one way or the other. We have the gate, which is the control input, and the body, which is the connection to the actual P-type substrate. So P-type means it's doped with P-type ions, usually boron. And then we have some N-type areas here that are typically doped with arsenic. And when we put a charge on the gate, we can see this as a capacitor. So between the gate is a metal layer, it's insulated with a layer of oxide, and then we've got the P substrate and then another metal connection here. And when we charge that up, we change the electrochemical properties in the channel region, and we allow current to flow between the source and the drain, or the drain and the source. And typically, to actually make this work on the chip, we need to connect the body to either the source or the drain. So this body will end up connecting up to the source or the drain, depending if it's an N-type or a P-type transistor. So why MOSFETs? They're easy to manufacture in volume. So using these mask patterns, that's part of the huge setup cost. We can expose silicon in special ways to build up these layers that form the MOSFETs. We can make tiny MOSFETs for digital switching, we can make big MOSFETs for power switching. And MOSFETs have become the basic building block of modern electronics. So let's have a look at how we would make an NMOS inverter. So this is straight out of that VLSI book, which I said was a bit dated, but it still shows how these things work. If we have a 0 coming in here, the gate is not charged, so the MOSFET, the N-type MOSFET, is not conducting. So this pull-up resistor pulls up the output. So if we've got a 0 in, we get a high output. And if we charge up the gate, change the channel properties, now the electrons can flow, and that pulls this down. So then when the input is a 1, the output is a 0. One of the problems with NMOS is that when we turned this on, this pull-up resistor is always dissipating a tiny bit of heat by being connected directly to ground. And as we know from our computers and our phones, they get hot in use. Dealing with the heat and excess heat is one of the problems. And when we've got millions and billions of these transistors all packed together, even though the amount of energy dissipated for each one is small, it adds up. So one of the innovations led to complementary MOSFETs, where you basically, instead of having that pull-up resistor, we replace it with a P-type MOSFET, so that when we want it when we want something to be high, we can pull it up with a switch instead of having pull it up with something that is we can't get rid of later. So this leads to efficiency gains. So let's move on to how you make a chip. You need to make these pattern files that you send off to the factory. and those pattern files the file format is GDS2. Now, the way that you end up with those GDS2 files is pretty much up to you. You can even draw stuff out with hand in Microsoft Paint or Inkscape or whatever you want. You can write Python programs to generate these patterns. But the way that we'll be doing it in this course is using a tool flow called OpenLane, which we'll get to in a later section, that puts together all these standard cells, merges them all, and then exports out the separate layers in a form of a GDS2 file that we can send away to the factory. And the factory takes those files. They've got to prepare the masks, which is these the patterns with tiny holes cut in them, so that when we shine ultraviolet light or blast ions down through them, we form patterns on the surface of the chip. So if you want to find out more in detail how this works, then I'd recommend this talk by Sam Zalouf at Hackaday SuperCon. He developed a home IC lab, but just talking through it very quickly, you have your prepared wafer, which would be of, say, P-type silicon. We coat it with photoresist, bake it, then we put the mask on, shine ultraviolet light down through it, develop it, and then we can wash off the parts that have been exposed to the light. And then we've got this pattern that's been transferred onto the wafer that we can then do a process. So we could etch through it to cut stuff away. We can grow levels of oxide or polysilicon or deposit metal on there. And by doing these in a sequence of processes, we can build up a three-dimensional structure that actually forms the working parts of the chip. So this is something that I didn't really realize until I got more into this, is how three-dimensional these structures are. And this is straight out of Wikipedia, and this is what the SkyWater 130 standard inverter looks like. Here's another look at the three-dimensional structure. So this is a cross-section here, and we've got this bottom layer is where all the transistors are. So that's where all the work is actually done, all the switching. But to actually connect them together into a working circuit, we use all these other levels. So if we start down here, we've got the gates and the diffusion layers for the MOSFETs, and then we've got all these different metals, metal 1, 2, 3, 4, 5, 6, that build up all the interconnections. And in the SkyWater 130 process, we have up to metal 5. So metal 1 is used in the cells, and then we can use metal 2, 3, 4, and 5. So it's like a 4-layer circuit board to join all these things together. So we've talked about the process design kit, what is in it. We've got a whole load of stuff. We've got about 75,000 files when it's extracted, 3 or 4 gigabytes of files. That includes design rule checks, behavioral models for the analog and digital cells, all the standard cells and their timing models, SPICE models that let us model everything. Really a huge amount of stuff in there. We don't really need to know all of it, but having a bit of a familiarity with the library can help, and that's one of the things that you'll be doing in the first 2 projects. So my experience so far has all been with the high density standard cell library, although the high voltage cells are used in the pad ring, the way that the chip talks to the outside world with the ins and outs. But you can also use cells that are optimized for higher speed or lower power, and it's all a trade-off. So maybe the high-speed ones are larger, so you end up with less space available for your design, but it can run faster. Or maybe you want it to be lower power, but then maybe it won't run quite as fast. And this is a cross-section of the Sky 130 process in more detail. So we've got the P substrate, and then we've got the diffusion. So we could, that's how we would make the active regions of the P or N MOSFET. We've got the polysilicon gate. We've got local interconnect and the local interconnect via, and then metal 1 and the metal to local interconnect via. And that's where the standard cells are built. And then we've got, as I said, this 1, 2, 3, 4 layers of metal with their associated vias to connect this all together. This is from the PDK Read the Docs, and we've got 33 layers, and we've got all these ones here are for that bottom set for the standard cells. This is used for the connecting everything up, and then this is used for the packaging, which we'll get onto when we look at the Skywater shuttle with eFabless. So a quick note about files. The most important ones are the GDS files. Those are the ones that we end up generating and sending to the factory. And then we'll be working a bit with def and left files. So once you have millions of cells in your design, loading up all of them and all their internal detail is a real struggle for your computer, even if it's a powerful one. So we have this abstracted view, and that's a def file. So you'll get like where things are and where they're inputs and outputs, but not information about what's actually inside them. And if you want to get the information about what's inside all those cells, then you also have to load the equivalent left file. Here's an example of a DRC rule. In my Hackaday talk, I said it was my favorite one because I thought it was a really cool one, but actually now having gone through the process, it was one of the most annoying ones because they were difficult to get rid of. But when we built our gate, which is sensitive to electrostatic shocks, it can be destroyed with a high enough voltage, and we've built up these interconnected layers, if we end up with a long enough wire, we basically made an antenna connected to this sensitive gate. And then in the flattening and polishing processes of building up these subsequent layers on the wafer, we can end up charging up one of the connection lines too much that then electrostatically destroys the gate, and we destroy the chip in the process of trying to make it. So we obviously want to stop that, so we can have a rule that basically checks the length of these antennas, and if they're too long, raise an error. And then you have to fix that by either making the line shorter or adding a protection diode that can dissipate that electrostatic, the buildup of charge on those antennas and dissipate it into the substrate before it can damage the gate. So let's take a look at some of these standard cells quickly. I'm using a tool called K-Layout, and I've just loaded all of the cells in the high density standard cell library. So let's take a look at inverter 1. And we can see here's the N channel MOSFET, the P channel is slightly bigger. Here's the input A, and that connects to this polysilicon layer here, which forms the gate. And then we've got our output here, and if we measure this, we can see that the gate length of the Sky 130 is actually 150 nanometers. Let's just take a look at something else. Let's take a look at, actually one thing I want to show you, let's take a look at inverter 8. Shows a new top. So initially I thought this meant that there were 8 inverters with 8 inputs and 8 outputs, but actually it means that it's just one inverter, but it's got 8 times the drive strength. So maybe it's driving a high fan-out signal that connects to lots of things, it needs a higher drive strength. And one interesting thing you see here is this, this distance here. All the standard cells are on this grid, so that lets you connect them one next to another. That creates these power and ground strips, and makes them very modular. Let's take a look at one more. Let's take a look at a 2-input NAND gate. There we go. So we've got our A and our B input and our Y output. So it's quite an interesting thing to have a look through and to get an understanding of how these things work, look at the different layers that stuff is on, and that's something that you'll be focusing a bit more on the 2 projects associated with part 1. So just to finish, let's talk a little bit about the node or the process. What does this 130 mean? Because I was sure that the 130 had to map to something physical on this chip, and it used to. It used to be that the node meant the half pitch and the gate length, which used to be the same number. So the gate length is that distance that I just measured, the 150 nanometers, and the half pitch is the distance, the minimum spacing on the metal layers. But as time has gone past, those numbers have drifted apart from each other. And Sky 130 is on a hybrid 180-130 node or process. And that means our gate length is actually 150 nanometers, like I just showed you. So that 130 doesn't really relate to anything specifically. It's just the name of the process that the factory uses to deliver chips at that scale. 130 is quite old. It's still very useful though. Europractice ASIC service shows that half of their output is 130 nanometers or bigger. So, and the fact that it's a bit older also makes it a bit cheaper, which is one of the reasons why it's been made available to us by Google, because it makes it more affordable for them to sponsor this sequence of shuttles. So that's it for the first part intro. I hope you enjoyed it, and good luck with the first 2 assignments.